recording. Yeah, so that's available on Canvas. And then I also posted a really short summary of regular expressions as we've talked about them. Again, regex is enough to fill a book, maybe a course, but anchors, wildcard matching, throwing things in parentheses to put them in registers, and so on and so forth. So that's kind of a half-page synopsis of what we've done. All right, so those are available on there. Since I started recording late, I'll mention again, make sure you do your SLP upload by Monday morning at 8 a.m. to get 50 out of your 100 points. All right, how's Zenity treating you? Has anybody gotten Zenity running on a Mac? Okay, cool. There's some people who are trying to figure that out, so I think they're going to post questions on Canvas or Discord. But yeah.
I did just want to ask a little question about regex. So
yeah.
You've got the two anchors for the start and the end of the line. Can you use both of them to, like, say, I want the whole line to match this pattern?
Yeah, you could say caret, bunch of stuff, $sign. That'll require that the entire line matches that pattern exactly. Okay. Yep, it's exactly the right way to use it. All right, so I want to talk about, actually I want to talk about PA4. And then we'll talk about SED. And let's go ahead and look at the modularized form. So when we wrote out some flowcharts for this, right, we were thinking about breaking this thing down into pieces, and we started with a SuperDuper GetCar that pre-processes your input one character at a time. SuperDuper GetCar does not build a phrase. It does exactly what GetCar does with a little bit of extra functionality. The extra functionality is let it get converted to uppercase. Any kind of white space gets changed into a plain old space. And if GetCar pulls up a character that we're not interested in, like a parenthesis or a dash, it gets the next character. And if that's a character we don't care about, it gets the next character. So our SuperDuper GetCar is basically GetCar, but it skips characters we want to skip, changes white space into a regular space, and converts to uppercase. And that's really the only difference between that and GetCar. So this is what we were calling SuperDuper GetCar, right? It's a custom GetCar function, does those things. So get a character. If it's one of these characters that we're supposed to ignore, get another character and go back to the top of this while loop. So this loop basically ingests from standard in until you have a character that you actually care about, right? Or you've hit end of file. I did not use is space in here. All I did here was change a new line to a space. But if you want to do this in general, right? If C is a space, change it to a plain old space, and then pass it to 2upper and assign the result back to C, and then return C. And this is legal. A lot of people did something like, C2 equals 2upper C and then return C2. If that's clearer, that's fine, but it's perfectly acceptable to assign a value to a variable that's being used elsewhere in that statement, right? Just like in here, we're saying if C is a space, then we're going to change C to something else, right? This works just as well. So we talked about breaking up our main program into something like this, read a phrase, save a phrase, and keep doing that until you hit the end of the file, and then sort, and then print. So kind of a 4-piece main program. And the first 2 pieces are in a loop, and that pulls in your phrases and saves them in your dictionary, right? And reading a phrase means look for the start of a phrase, look for the end of a phrase, take everything in between, throw it into an array, right? And as we're pulling things in, we're using the SuperDuper GetCar, so it's converting to uppercase and all that other nice stuff, right? And then save a phrase says look in the dictionary for the phrase. If you find it, bump up the tally count. If you don't find it, add the phrase to the end of the dictionary with a tally count of 1. And while you're at it, make sure that you don't have more than 1,000 phrases stored, and do something reasonable if you do, and so on and so forth. And then bubble sort, and then for loop that prints out your dictionary. Right. So that was the proposed structure when we flowcharted the pieces of this. So my main.c basically does the same thing. So a pretty minimal comment block up here. Includes the prototypes of the functions we're going to use, and then here's the whole main program, right? And half of it is declaration of variables. While read phrase buffer dictionary length equals tally, that's that loop right there, right? So read phrase reads the next phrase from standard in, stores it in buffer. Buffer is a 201 character array. And then tally says look for the phrase in the dictionary. If you find it, bump the tally. If you don't, add it to the end of the dictionary, set the tally count to 1. Since calling this tally can potentially change the length of the dictionary, I have that function return the new dictionary length. So inside main I can say dictionary length equals, and I tell it to do this tally. So what are the arguments to tally? The phrase that's in question, the dictionary, the count array, and the number of things in the dictionary and count arrays, the dictionary length. And read phrase has been set up, I should have commented it up there, it's been set up to return 1 if it successfully reads a phrase, and 0 if it hits end of file. So I can say while read phrase, and if read phrase reads a phrase, it'll return a 1, my while loop will continue. I'll store that in the dictionary and try again. When we hit end of file, read phrase returns a 0, we exit the while loop, and then we simply do a sort, and we do a print. And both of those need the dictionary itself, the array of tallies, and the number of things in that entry. So that's your main program, and that probably gets written last, right? Because you can't really do anything with this until you have all these other functions written. But I want the idea of this in my head before I start writing anything. I want to know what this tally function is going to do. And once I know what I want it to do, I can define what I want it to take as inputs and what I want it to return. I want to know what the sort's going to do, and then I can define what the inputs are and the outputs.
So use a pointer on the buffer instead of.
Yeah, I could have done 201. So read phrase is the workhorse, the phrase builder, right? And that's, I have a bunch of read related functions in this file called read.c. So read phrase is really this. So phrases start with a non-space, non-punctuation character and end right before a punctuation character. So grab the first character, c equals my getCar, and then I made an isTerminator function that takes a character and tells you if it's a terminator or not. Returns 1 if it is, 0 if it's not. Is space is a built-in C type. So while our character is either a space or a terminator for a phrase, we have not found the start of the phrase yet. I do a check to see if we're at the end of the file. If we are, we just return 0 and we say we're done. We've hit the end of the file. Otherwise, get another character and go back and try again. So all of this is looking for the start of a phrase. Right? Get another character. If it's a space, we're going to keep going. If it's a terminator, semicolon, colon, period, exclamation mark, etc., we're going to keep going. Right? Get a character, check again. When we finally get the start of a phrase, the letter H, for example, right? It's not a space, it's not a terminator. We're going to exit that while loop. And C is going to be the first character of our phrase. So we save that in the first position in our output array, right? I got initialized to 0. And now we go into a loop which saves elements in our phrase. So get the next character. If it's not a terminator, save it in our array. Do something to make sure our phrase doesn't get too long. And I should have done 201 here, right? Get the next character. If it's not a terminator, save that in your output array. Get the next character. This will just keep looping, ingesting characters with my GetCar and saving them in this buffer variable, this output array. And if I gets to be too big, I just bump it back down one spot so I don't run off the end of my buffer array. And then when we find a terminator, we write the null at the current position in our output buffer, and we return 1 saying we found a phrase. And that phrase is stored in buffer in our main program. We'll take that and then use it to tally up. So that's the read phrase piece. My GetCar we already looked at, right? That's SuperDuper GetCar. Is terminator is just a if statement, right? And you can do this as a bunch of if statements. You could do it with a switch. You could do it with one if statement with ors inside, whatever you like. And I didn't need to check for EOF because I actually do that in the loop. But mainly I'm checking for one of these characters that we're going to use to end a phrase. And I don't need to check for parentheses and quotation marks and dashes because I'm never going to see those, right? I'm never going to call isTerm with a parenthesis because parentheses don't exist to me. Why? Because my GetCar function will not return a parenthesis, right? That's why we made a SuperDuper GetCar. Because if I'm always calling my GetCar instead of GetCar, I don't have to think about parentheses and quotation marks and dashes. I'm never going to see one, right? So we're taking that functional behavior and we're throwing it somewhere else. And we're saying, you know, GetCar is never going to give me one of those things. I don't have to think about it. So that's it for the ingestion. And then the tally function is its own beast. But not too bad. So here's the thing that we're storing in our dictionary. Here's the dictionary itself. Here's the array of tallies, how many times each phrase occurs. That's the number of things in our dictionary so far. So first thing we do is we search for our phrase. So it's a for loop. I goes from 0 to dictionary length minus 1. And if our phrase that we're storing, which is in buffer, is exactly the same as the ith entry in the dictionary, then this phrase already is stored in our dictionary. We simply have to update the tally. So plus plus count bracket I, right? That increases the number of times we've seen that phrase by 1. The dictionary length hasn't changed, so we just return dictionary length. And the other option is we go through this whole loop and we never find that any entry in our dictionary is equal to our phrase buffer, right? So this if statement never fires, which means we never do this return, so we come out of the loop. If we get down here, it means the phrase is new. So first thing we do is check the dictionary length. If it's already 1,000, we don't save the phrase. We just return and say the dictionary still has 1,000 things in it. So we're ignoring that phrase, but we're still going through all the processing. We're not exiting our main loop in the main program. If the length is less than 1,000, there's still space to store a new phrase. So that new phrase goes at entry dictionary len, right? This is this starting arrays from 0 business. So copy our phrase into that location in the dictionary. Set the count at that location equal to 1. And then after you do that, increment dictionary length by 1. So that's the post increment, or we could do a dictionary len equals dictionary len plus 1 after that, and then return that new dictionary length. So in main, after we've called tally, dictionary length would be 1 more than what it was before we called tally. So that's how the dictionary grows, and that's all there is to the tally function. And then sort, this may be the longest function. So bubble sort, we talked about bubble sort. So pass 1 is the outer pass, which runs dictionary length times. Pass 2 goes up to dictionary length minus 2 and compares entry pass 2 with entry pass 2 plus 1. And if the length of pass 2 is bigger than the length of the entry after that, copy entry pass 2 into a temporary, copy pass 2 plus 1 into pass 2, and then copy the temporary into pass 2 plus 1. So swap those two entries, the one at pass 2 and the one following that, and then swap the corresponding entries in the count array. So that's just an array of integers, so temp equals count pass 2 comes from pass 2 plus 1, and then pass 2 plus 1 gets the old value of pass 2. And that swaps them around, and do that all the way through from beginning to n minus 1, and repeat that pass dictionary length times. That should leave you with a sorted, length sorted dictionary. And then the print code is just a for loop, as we've said. Print out the count value and then print out the dictionary entry. So there's no globals in here, right? These main variables are the dictionary length, and the count. And those are variables inside main, and they're passed to functions that need to use them. And the only one that has to get modified is the dictionary length, right? I mean, the dictionary gets modified, but it's an array. So if a function changes values in that array, those changes exist when we get back in main. So
Is it better practice to have as many local variables as you can, or is it better just to, like, I did them all global, because I don't want to worry about it? But
it's best practice generally not to have global variables at all.
okay. So they're not
Right.
efficient?
The problem is they can be error prone. I mean, obviously, if you keep track of it and you don't make mistakes, then they're not error prone. But in general, you know, if you have a global variable, especially if you have a global variable with something named like I, for example, right? It's really easy in your function to have a local variable named I and then think that you're accessing the global variable, right? Or to think that you're accessing a local variable, but you didn't actually declare it, and you don't get any warnings from the compiler because it's a global. And so you initialize I to 0, and you just change the value of this global variable that 5 other functions depend on. So particularly if you're programming in groups, right, or teams where other people are sharing code, globals are just really hard to keep straight. So they're kind of generally frowned on. Tactical use of 1 or 2 once in a while in the right place for your own stuff makes perfect sense sometimes. But as a habit, I would try to avoid them as much as possible. And the mechanism that we have in most languages for avoiding globals is that we can pass things to functions, right, as arguments. And sometimes it's a pain because we might have 15 variables that we need to pass to this function, pass to that function, right? It's getting a little unwieldy here because we always have the dictionary array and the count array and the dictionary length, right? But this is what structures will do for us, we can create a structure that has, 15 variables in it, and have basically a single variable of that structure type. And now we just pass that one variable to a function, and it's got access to all those 15 variables that make it up. And that's what we'll do in 222, is we'll rely heavily on structures. But then that will segue in 223 into the idea of objects and classes, where we'll have a single variable that not only contains, 15 different variables, but, several pieces of code, several functions for manipulating those variables. And they'll all be associated with a single variable that happens to be a variable of this particular type of object, this class. So we're really moving towards object-oriented programming starting in spring. All right, so questions about that. Does that make some sense? It's not uncommon, at least for me, when I'm writing code, to get a lot of code written, get, several hundred lines into code development, and then push everything into a backup directory and start again. The reason I would do that would be because I would realize something different about how I want to organize my functions. I might have thought about it in terms of this structure, and as I started coding it, I kept bumping into the fact that I really should have been doing that structure instead. And after some point, it's like, I really need to just redo this. And you go back and you start over. But while I'm developing this stuff, right, I usually have either on paper or in a README file or something, information written down about what all of this means, right? What exactly does read phrase do? Yeah, it takes a char star and it returns an int, but more than that, right? What is this thing that I pass to it? How is that changed? What are all the details? What are the edge cases? What are the assumptions? That kind of stuff. And this goes into the idea of this comment block that I'd like to see in the beginning of each of your functions. Something we'll push more in 222, right? Think of your function as something you could write a manual page for, right? If you were writing the printf function, this is all, description of what that function does, right? If you're writing an fgets function, this is description of what fgets does. And unless it's a function you've written 100 times, and there are functions like that, you really want to make sure you understand what's going into it, what comes out of it, what are the assumptions, what are the side effects, right? All of those details. And if you've got that totally nailed down, right, you can write code that uses that function. And then if you find the function doesn't do something exactly right the way that you were thinking it would, you have to modify the function to make it match. Or maybe you decide the function does something different. Now the things that use the function, you have to rewrite those because you thought it was going to do X and now it does, Y instead. But the more you can pin this down ahead of time and sort of picture how the pieces are going to go together before you open VI, right, the more comfortable it will probably feel as you're writing the code to use these functions and to actually develop the functions. So none of this really works very well in PA5 because PA5 is the script, and scripting doesn't usually modularize as well. It can, right? You can break things into functions and stuff, but it's just not that deeply nested of an assignment. PA5 tends to be kind of linear. Do this, do this, do this, do this, we're done, right? Whereas PA4 was like, do these things in a loop, and if this happens, do these other things, and now go on to do these other things, then go back to the beginning and do that again, and it's much more convoluted like that. So the hierarchy, the modularization makes more of an impact on that. But winter quarter, right, we'll definitely be writing a lot of C code, and it'll be stuff that has a lot of layers of behavior to it. And so we get a lot of practice at breaking things up and modularizing, kind of out of necessity. All right. I need to tell you a trick to use with Zenity if you're running it on Cygwin or a Windows system. Yeah, go ahead.
Talk about the class during the winter season. So if I cannot take the class 222 during the winter, the only chance I can take it is next year.
Yeah, it's only offered in winter, and it's a prerequisite for 223 in spring. So come and talk to me if you've got a scheduling issue or some other issue about that. So if you're using Zenity on Cygwin, you may or may not have discovered this yet. Sometimes when you build your reservation file using the results of Zenity, you end up with these funny characters in there that if you try to look at them in Unix, your file comes out looking really strange. There's a trick we can use to deal with that, but I'm going to talk about it tomorrow because I want to talk about sed first, and sed is what we use for it. And I want to pull a file from my Windows partition so I have something to actually work with and talk about. But if you're struggling with weird characters in Zenity under Cygwin, let me know, and I can give you a heads up on how to deal with it. But we'll talk about it in general tomorrow. All right, so let's talk about sed. So sed is I don't know how big the man page is. It's not too bad. Sed is a stream editor. It's nominally for doing things that we could do with VI, but instead of doing it while we type commands in VI, we can put our commands into a sed call as command line arguments, or we can put them into a file and point sed to that file, and it will read standard in, apply these edits, and produce the output on standard out. Okay, or we can give it a file to read, an input file, and it will apply the edits to that and then produce the output on standard out. So let's just do editing without having to actually type interactively. Okay, it's a stream editor, it's a batch mode editor. And we started playing around with this a little bit. So here's a foods file. So I can say substitute fruit with Fruit Loops fruit, right, in this file foods. And everywhere that the word fruit appeared, it got replaced with this. Right, so that's doing a substitution globally across a file. Or I could substitute a space with a bunch of spaces. Right, and my first space on each line gets replaced with a bunch of spaces. And if we wanted to replace every line with a bunch of spaces, we can do a /G switch just like we do in VI, and it does that. So that's pretty useful in itself, right? It saves you from going into VI. But of course, you know, we go into VI and say $1, substitute space with a bunch of spaces globally, and the same thing. Right? And this doesn't change the file. This is just reading from the file and producing the output on standard out. And if we don't put a file name, it just reads standard in, applies the edit, and produces the result on standard out. But sed will do a lot more. Sed is really kind of a programming environment in some way. So let me talk about sed in general, and then let's look at some things that we can do with it. So here's the basic way we run sed. We say sed, and then we specify some sort of program, and then we specify a file. And if we don't specify the file, it reads from standard in. And our program can be, you know, something short like quote substitute slash space slash bunch of spaces slash g. Right, that's an example of a program. If our program is more complex, we can actually put our program into a file and say sed-f and then put in the name of that file containing the program. So our program file, and then the file that we want to read. And the simplest program in the world is just an empty program. Just quote, nothing, quote. So if I just say sed, quote, quote, so here's my foods file that I'm going to be messing with for the next few minutes. Okay, so it's the food, it's the type of food it is, it's the color, and it's how expensive it is. So sed, empty program, foods, just reads from that file, copies it to standard out. Okay, the program basically says don't do anything special. So it's kind of like the cat function, right? It just reads from a file, sends it to standard out. And normally when sed reads a line from a file, it will copy it to standard out. If I say sed-n, that says don't copy the input to standard out as you're reading it. So if I do this, I get no output. Right, if I do this, I get no output. -n switch says don't copy standard in automatically to standard out, or don't copy the input lines we're reading automatically to standard out. Okay, so hold that in mind. So what does a program look like? So it can be an instruction, or it can be an address followed by an instruction, or it can be an address, comma address followed by an instruction, or it can be a slash and a regular expression followed by an instruction. So it can be just a plain instruction, like substitute slash this with that. Or it can be an instruction that's preceded by an address, and your address can be a number. So it could be line 2. Or it could be a $, which means last line. Or it could be a range of addresses, starting line number, ending line number, with a comma in between. Or it could be a regular expression in between two slashes, which means if this regular expression is found somewhere in the current line, then do whatever the instruction says. So instructions. First instruction is P. That means print. So sed-n, quote, quote, foods, reads from the foods file, applies this empty program, right, with no instructions in it at all, and the -n says don't copy what you're reading to standard out, so it doesn't produce any output. Now, if I use the instruction P, it reads from the foods file. It applies the instruction to each line. P says print the line that you just read, and so we get a copy of the file out. Let me make a smaller foods file. Okay, so we'll just work with this 3-line file for now. Okay, what happens if I get rid of that -n switch? Here's what SED's going to do. It's going to read the first line from the file. It's going to copy it to standard out, because that's what it does if you don't say -n. And then it's going to execute the program which says print the current line. So it's going to print that line that it just read a second time. Then it's going to read the next line from the input file. It's going to copy it to standard out, because that's what it does if you don't say -n. And then it's going to execute the program which says print the current line. It's going to print that second line a second time. And then same thing with the third. So it produces each line from the input twice. So let's go back to the -n version. So this is just reading from each line, executing the program which says print. Okay, if I say 2 space P, right, that's an address followed by an instruction. It says, if you have just read the second line of the file, print that out. Since the -n switch is there, it's not going to copy the input to the output normally, but when it reads the second line, which should be banana, that'll say go ahead and print it. So there's a way to print the second line of the file. If I say 2, 3, it'll execute the print instruction anywhere between lines 2 and 3 in the file inclusive. So that will print out the banana and the Oreos. If I don't know how many lines I have, I can use a $sign, and that means the last line of the file. Right, so all of this stuff is parallel in Linux, right? So this is all stuff that we see in VI. You can use a $sign for the last line, things like that. If I do a /fruit, right, that's a regular expression which looks for fruit in the input line. So it should print out the first 2 lines, apple and banana. Fruit doesn't appear on the line with Oreo, so it should not print the third line. But those first 2 lines, it finds that regular expression, so it executes that instruction which says print. So it prints out all the lines that contain the word fruit. Alright, if I just do sed ;f, remember, without the -n, each line that it reads from the input gets copied to the output. So the instruction doesn't say to do anything, but the default behavior is still read each line, copy it to the output. So another command I can use is quit. So P is print, Q is quit. So I can say line 2, execute the instruction quit. And so it reads the first line, copies that out by default, reads the second line, copies that out by default, and then since it's the second line, it executes the instruction that I said, which was quit, and sed exits at that point. So that prints out the first 2 lines of whatever file I feed it. Okay, so this is kind of a quirky way to manipulate things, but is it making sense so far? Not necessarily why we want to do this, but just the mechanics of it. Okay, so let's go back to our foods file, so we have more input to mess with. And I have a 3-line program here. It says line 3 print, line 4 print, line 4 quit. Okay, so this is a more complex program, so instead of just specifying it on the command line, we're going to say sed-f and then give it the name of that program, P1. And I'm going to do -n so it doesn't copy output by default. And let's run this program P1 on the file foods. And it should, at the third line, print that out, Oreos. At the fourth line, print out kiwi, and then it should quit. So we should get 2 lines of output, Oreos and kiwi, like so. And if I don't have that -n switch, then in addition to what we just saw, each line that it reads will get copied to the output before it executes the program. So this reads the first line, prints it out, reads the second line, prints it out, reads the third line, Oreos, and prints it out, and then executes the print instruction, so it prints Oreos again. Reads the fourth line and prints it out, that's the first kiwi, and then, since line 4 says print, and it's the fourth line, executes the print instruction, prints kiwi again, and then, since it's line 4, it executes the quit instruction and said exits. All right, next instruction A, which means append. So here's another program, P2. P2 says at line 2, do the following. Append, this was added after line 2. And then it says print without an address on it. So each line that it reads, it will check to see if it's line 2, and if it is, it will add that to the output. And then regardless of what it read, it will go ahead and print that line. So if we run that with the -n, we're usually going to stick with -n so we don't automatically copy the file to the output. Let's execute this program P2 on the file foods. And you can see it read the first line and it printed it. It read the second line and it printed, but the second line had this extra thing appended to the end of it. So that's a 2-line SED program that lets us append something after a certain point in our file.
Does
Yeah.
append automatically go to the next line?
Yeah, it appends it after the line, so it appends it as a new line. Yeah. Okay, yeah. And we can also do an insert. So I is an insert that inserts it before the current line. So now I have a 3-line program, P3. Search for the pattern cookie, and if you find it, insert before that line, here comes a cookie. And then search for a cookie, and if you find that append after that, that was a cookie, and then print the current line. So it turns our file into this. And if you wanted to do this in C, it would be kind of a pain. Right? You need to read each line, you need to save it in a buffer, you need to somehow search for a pattern inside there, and then if you found it, you need to print out something before, and then print your line, and then print out something after. Otherwise, just print out the line. Right? And then if you want to do something different, you'd have to change your C program accordingly. And for us, it's just 3 lines, right, using these 2 instructions. Insert and append, and then the print. All right, so we'll keep building on this tomorrow.